Section 12.8, heat and phase change, latent heat. So if we want to talk about phase change, it helps to highlight the different phases of matter. So there are three basic phases, are gas, liquid, and solid. And more often than not, we switch between gas and liquid and solid. We can technically switch from solid to gas, right? You can condense a gas into a solid or sublime a solid into a gas. An example of that would be dry ice. It immediately goes to gas and skips the liquid phase, but most often will be on this other side of this cycle, right? Where you can have a solid like ice and you can melt your ice and it becomes liquid, or you can freeze your water and it becomes ice, it becomes solid. The liquid, similarly, it can evaporate into gas, or you can condense the gas into a liquid. So these are the different directions to go, and it's important to understand the terminology going back and forth between them because it will help you in translating various problems to understand what is going on. Now, the interesting thing is that sometimes you can add heat to something without the temperature changing, right? So you might have a glass of iced tea out on a nice, warm, sunny day, and the iced tea is at the temperature of ice, 0 degrees Celsius, while the air is around 20 degrees Celsius. What's going to happen? Well, it turns out, as long as you have a little bit of ice in there, the ice will melt, but your iced tea will still stay at that nice cold temperature, even though it's getting heat from the outside environment. So what's going on here? Well, a really nice illustration of this is this graph. This graph shows temperature as a function of heat. So as you add more heat, what does the temperature do? The interesting thing here is during a phase change, the temperature of the mixture does not change, provided the system is in thermal equilibrium. So while the water is boiling, the temperature stays constant at 100 degrees Celsius. Once all of the water is boiled off, then the water vapor is going to warm up. If we start decreasing the heat, right, the water can cool down until it becomes ice. Once you get ice forming, it's all at 0 degrees Celsius. There's no temperature change. But once it's all frozen, you can actually cool your ice further below 0 degrees Celsius. So you can go either way on this. But the important thing to note here is we have temperature changes here where the substance, whether it's solid, liquid, or gas, but it's purely one of those three, where the substance itself changes temperature. But when you have a mixture of solid and liquid or liquid and gas, it's not changing temperature at all. Let's check out a conceptual example that takes a look at this. So this is saving energy. Suppose you are cooking spaghetti for dinner, yum, and the instructions say boil pasta in water for 10 minutes. To cook spaghetti in an open pot using the least amount of energy, should you turn up the burner to its fullest so the water vigorously boils, or should you turn down the burner so the water barely boils? I want you to think about that for a moment, come up with an answer, so you can go ahead and pause the video if you will. All right. So this is an interesting one because my instinct says, okay, if I just want to cook it, like, great, let's crank that thing up. But it just says to boil for 10 minutes. And as long as the water is boiling, even if it's barely boiling, we know it must be at that 100 degrees Celsius. So that means it'll be the same temperature, whether we have the burner turned up all the way or just at the point where we're barely boiling. Now, if we dip below boiling, then it might dip in temperature as well. But as long as we keep it boiling, even if it's barely boiling, it's in thermal equilibrium throughout, then that will be enough to cook our pasta and save us some energy in the process. So what is going on in this phase change? Where is the heat going if it's not going into changing the temperature? Well, the way we describe that is by the heat supplied or removed in changing the phase of a substance. So in order to change the phase of a substance, the heat that's necessary Q is given by m times L. So m is the mass of the substance. That depends on the substance itself. L is the latent heat. So this is like our specific heat capacity, but it has to do with the phase change. And it'll be specific to both the material and the type of phase change we have going on here. The units of latent heat are a little bit simpler. If you solve this for L, you get Q divided by M. So you get joules per kilogram will give you your L value. And I'm sorry, I know we've seen L before with things like length, even in this very chapter. So you just have to pay close attention to the context in order to keep it straight. You might, on your equation sheet, want to label that this is the latent heat. This is not length. So this latent heat, again, like specific heat capacity, is something we look up in a table. So let's take a look at an example in the table. So here are latent heats of fusion and vaporization for a variety of materials. So with fusion, that's going to be going back and forth between solid and liquid, right, in either direction. So you can think of it, if you have a liquid and you freeze it, then it is fusing together to form a solid. Versus vaporization is the other latent heat we have. So if you think of something vaporizing, that's like a liquid turning into a gas. But it turns out we can use this for it going the other way too. So liquid to gas or gas to liquid. And that's what you want to note with these. Now we have a bunch of substances. The one we will use more often than not is water, the one at the bottom. And there's a clue here as to what phase change is happening because they give the melting point and the boiling point. Right? This is the exact temperature at which these phase changes occur. So for water, the latent heat of fusion, the point at which water freezes or ice melts, is 0 degrees Celsius. So this will be the temperature anytime we are changing phase in a fusion process. So LF there. If instead we're boiling our water, we know we're going to be up at a temperature of 100 degrees Celsius. And note, these are very exact values. The Celsius scale is defined based on them, so you don't need to worry about them limiting your sig figs. So that's our temperature for if we're boiling our water, and we're going to use a different latent heat in that case, the latent heat of vaporization. So this is a really important and useful table to keep track of all the different things. And like I said, water is going to be the one that we use more often than not, so hopefully you are up on that. All right. Let's look at an example of this. So example 14, ice cold lemonade. That sounds good. Ice at 0 degrees Celsius is placed in a styrofoam cup containing 0.32 kilograms of lemonade at 27 degrees Celsius. The specific heat capacity of lemonade is virtually the same as that of water. After the ice and lemonade reach an equilibrium temperature, some ice still remains. Find the mass of the melted ice. Assume the mass of the cup is so small it absorbs a negligible amount of heat. All right, in looking at this problem, there are a lot of pieces of information packed into it. So let's see if we can untangle them in order to figure out how much ice has melted here. So first, they tell us that we have ice and they give us the temperature of the ice. Temperature of the ice is 0 degrees Celsius. Awesome. They also say it's in a styrofoam cup. That tells me that this is insulated, that we're not going to lose heat to the environment. And so this means we can use our heat gained is equal to heat loss equation. So that's really useful. Heat gain is equal to heat lost. Awesome. All right. Now we know this mass, 0.32 kilograms. That's going to be the mass of the lemonade. So M sub L there. Maybe that's a better way of writing it. All right. So we have our mass of the lemonade. Very good. And we also have a temperature of the lemonade, right? So that's another temperature. Notice these are both initial temperatures of, say, the lemonade or the ice. Lemonade, this would be ice. Now, does it tell us the final temperature? It doesn't give us any other numbers of degrees, but it does give us a clue. And that says after the ice and lemonade reach an equilibrium temperature, which first off, that's a clue. If they're at an equilibrium temperature, that means they're at the same temperature. So T final for the ice is going to have to be equal to T final of the lemonade. And it gives us this clue that some ice still remains. Now, for ice to still remain, that tells us the temperature that we have reached, right? The only way we can have ice exist is at 0 degrees or lower. And there's nothing here that's going to lower the temperature below 0 degrees. So that means the final temperature is going to have to be 0 degrees Celsius. That's a really important implicit information. It also tells us the mass of the cup is so small it absorbs a negligible amount of heat. So we can say that the heat of the cup is 0. In other words, we don't need to worry about it like we did with the calorimetry example, which is great. All right. So this is looking good. We can note, okay, the ice stays at 0 degrees Celsius. So what form of heat, where does the heat go in terms of the ice? The heat goes just into melting the ice. So with the ice, we're going to note that it is a phase change. And how do we describe the heat going into a phase change? That's going to be our ml. Now what about for the lemonade? Does the lemonade have a phase change? Well, it doesn't say the lemonade starts to freeze. If anything, the lemonade's melting the ice. But the lemonade does change temperature. So because it has this delta T, we're going to use the MC delta T equation to describe its change in heat, or the heat flow related to the lemonade. Now we have the mass, we can figure out the delta T with the 27 and the 0. What about the C? It gives us a clue on the specific heat capacity as well, right? Notice it says the specific heat capacity of lemonade is virtually the same as that of water. Aha! There's our last piece of information. We can look that up in the table. We'll be good to go. So let's take a look at that. Specific heat capacity, and we have water. 4,186 joules per kilogram per Celsius degree. Awesome. So with that, we can now solve away, right? We are going to again set up heat gained is equal to heat lost. What's gaining heat is the ice. It's starting to melt, versus the lemonade is losing heat. It is going to a lower temperature. So we describe that with ml, latent heat of fusion of the ice, is equal to mc delta T of the lemonade as it changes temperature. So the mass of the ice melted is going to be equal to the heat that is lost by the lemonade divided by the latent heat of fusion of ice, which we can look up in that table. And we would find if we did that it's 3.35 times 10 to the 5th joules per kilogram. That's the latent heat of fusion for water. And then for the lemonade, we have our specific heat, C, times the mass, times the change in temperature, which is positive. And so this calculation comes out to 0.11 kilograms. So once again, the total energy is conserved, we can account for the fact that the lemonade is losing heat and it has to go somewhere, so it goes into the ice melting. But we can be very precise in noting what sort of heat transfer is happening. Is it a change in temperature or is it a change in phase? And this brings us through the end of chapter 12, where we've gotten to see a lot about heat, the energy flow of heat, and how that relates to temperature as a whole.